I will talk a little bit about FLIR, who we are, where we come from, about the history of thermography, the future of thermography as well, and I will show, I've seen you have learned a bit about emissivity, about the wavelength, that is very good. So I will connect to that and go deeper into when do we use shortwave, midwave, long wave, some applications. So I will try to fill the next hour or close to an hour with some information on thermography. So just a few words about myself. I'm working with thermography for 21 years now. I'm a level 2 certified thermographer. I come originally from Austria, and I'm responsible for Central Europe. I'm the responsible sales manager for cooled high-speed cameras mainly. So just a few words about our company. FLIR Systems is a US-based company. We go back many, tens of years, I would say. And these numbers are not exactly right. We are over 4,000 employees now, so constantly growing business. Our main business still is thermography, and our instruments headquarters is in Sweden, near Stockholm, in Täby. So most of what happens with when we say instruments, it's basically all thermal cameras that are used in a lab, that are used for building diagnosis, for most applications, I would say. So all non-military, non-hunting, things like that. This should show a map where we are, but it does not look it does not look very good. Might be a compatibility problem. This is not my computer, so let's just skip that one. And as I said, our main focus is on thermal. Anything that has to do with infrared, midwave, shortwave, long wave, not only for labs, but also in everyday applications. So when you have a traffic light, you can use a camera. When you have a car you want to see at night, you use an infrared camera. So it's not always calibrated, it's not always measuring. Sometimes we only want to see something, like in firefighting, for example. If the firefighter goes in, they need to know where the hotspots are, where they need to apply water, where they need to cool a door or something like that. Optical gas imaging, I will talk a bit about that. It's quite interesting. That's a small part of thermography or of infrared technology, but a very interesting one. And you see many applications here. And when it comes to non-thermal, FLIR is also in gas detection systems, non-camera based, but simple handheld devices and in many different applications. So the history is also a bit a history of thermography itself. This has been taken in the 60s, this image. That's the King of Sweden. Back then there was a new camera introduced, one of the first, or the first worldwide commercially used camera. So non-military, really for commercial use. So they put it on a small truck. They were driving around, and wherever the truck could go, the camera could go. And as a display, you had a oscilloscope. You know those green oscilloscopes back in the 60s? Something like that. So it's brighter, it's warmer, it's darker, it's colder. That's basically it. And when we go into details, I don't know how many of you are working with thermography itself. The whole technology goes even further back, but this is commercial thermography. Some companies were bought by FLIR or acquired by FLIR. Inframetrics, that is how I joined FLIR in the late 90s. And here it starts getting interesting when it comes to price, because I will speak about cooled and uncooled. What is it? You have heard a little bit about it already. When it comes to uncooled cameras, the prices were dropping. So when you want to buy a camera today, even a small plug-on camera for your cell phone, it's 250, 300 euros starting. And this is only possible with an uncooled camera, because the cooler, the noise you hear outside a little bit, that's a cooled camera. So we have a Stirling cooler inside, and the price is always quite high with those. And in the late 90s, the first uncooled cameras came out, and this is when the price started to drop. And so the resolution grew, we got higher resolution, we got better systems, the cameras got smaller over the years, and the smallest one now is the FLIR 1 Pro. I have one outside, so I can show you later if you like. What's going on today? Sorry for the writing and so on. It does look different on my PC, but never mind that. We have our own lens production. So we produce our own lenses. We produce our own detectors. And this little thing here is 9 by 9 millimeters. And it's also in some cell phones. So if you have a Caterpillar S60 or S61, I think it's called, it has a FLIR core inside. So let's talk a bit about physics. You heard a lot in the last presentation, so I will not go that deep into details. But just to give you an idea, we are talking about mainly infrared today. I will talk about visible light a little bit. I will also show you how you can combine these. So we have a long-wave infrared camera, and we use the visual channel, so the visible light, to recognize patterns, to find objects and so on, and to overlay those two. So it's basically a multispectral camera. Unfortunately, we cannot hook it up to the projector, so I will show you on the screen in the end. And maybe if you want to come back to the first rows a little bit later, I can show you. I will inform you then. So this you already have seen. When we speak about measuring temperature, we usually go either in the 3 to 5 micron wavelength. So we have our visible light down there, a few hundred nanometers. Then we have near-infrared, short-wave, mid-wave, long-wave, as you have learned. We either use 3 to 5 or 8 to 14. Why do we do this? Because when you want to measure at room temperature, an object does not show up in visible light. So if we switch off the lights, we will not see anything here. But what happens if you heat up something? If you take a metal part and you heat it up to 600, 700 degrees Celsius, it will start to glow. So you will see temperature in visible light, but you need a high temperature. That's Wien's law. Basically, it tells you that the higher the temperature, the shorter the wavelength. That means we can use, in theory, we could use a visual system to measure temperature when it's 800, 900 degrees, something like that. We can use a near or a shortwave camera when we are at 200, 250 degrees Celsius. So the colder the temperature, the longer the wavelength has to be. This is why we typically consider everything above 3 micrometer as a thermal band. So what detector materials do we use? You have already seen this. Indium gallium arsenide InGaAs. This is the typical camera for near-infrared, for shortwave, up to 1.9 micrometer in that area. And then we can use, and this is the most commonly used in cooled cameras, InSpi, indium antimonide. So most of those cameras operate from 3 to 5 micron. Now we can use a broadband InSpi camera that goes down to almost 1 micrometer. Why would we do this? If you're looking at glass, glass is not transparent in the 3 to 5 area, nor in the 8 to 14. Glass is transparent down here. So you have a light bulb. You're producing light bulbs for cars or for anything, and you want to use a camera to see inside the glass through the glass housing. And then you use a broadband camera. So you can use a camera with a filter in the shortwave area. You can look through glass on hot objects. The first part now, I will come into midwave and longwave a little later in detail. The first part should be shortwave cameras, InGaAs. And then we will compare, let's say, midwave to microbolometers. Microbolometer is the object here. You have already seen in the presentation, it's a thermal sensor. It's quite slow. It's not that expensive, but it has some disadvantages. And again, the first part of the presentation should be near infrared and where do I use it? You have seen some applications now when it comes to crops, when it comes to the health of plants. We also have other, let's say, possibilities, many other possibilities. I will not go too deep into the camera itself. I have some cameras outside. You can have a look later on. But the in-gas detector is a very sensitive detector. It can be used uncooled, so we can operate the detector at room temperature. It does work. We can cool it down, or we can at least stabilize it a little bit. Then we get more precise readings out of it. When it comes to speed, 180 frames per second in full frame. And if you reduce the amount of pixels, you can go up to 17,000 frames per second. So if you have a very fast object, rotating object or something, the camera can go very fast. So where do we use it? What are typical shortwave applications? One thing, in visible light, we are much more influenced by, for example, fog. So a shortwave camera can see further, typically in most types of fog, than a visual camera or our eyes. Classic application that has been used for many years is tracking lasers, target lasers or something like that. So that comes from the military. And also a lot of money for research and development of those cameras is coming from the military. So this is a typical military application, but I will look into the non-military now a little bit deeper. Solar cell inspections. If you use a solar panel and you apply electricity and put it in a dark room, it will start to glow, but not glow visibly, only in near infrared. So you will not see anything with your eyes, but a camera in near infrared can see cracks, it can see broken parts of a cell or a module, and that's called electroluminescence. They do it today with visual cameras with a filter attached. So they use a filter to block the visual light and only let the near infrared through. The problem, how they do it today, the exposure time, the integration time of a camera is 30 seconds, half a minute for many systems. So you need a totally dark room. Then you apply electricity to the solar cell, and half a minute later you have a result. That's traditional technology. With an in-gas detector, it takes 1 millisecond, so 1,000th of a second. So it's a bit faster. Silicon, wafer inspections. In different spectral bands, silicon becomes transparent, so you can look through the wafer on the or through different layers of the wafer. Agricultural, again, interesting for today's surrounding here. Water is not transparent in near infrared, so you can easily spot water. I can show you here. That's a plastic cup or a glass of water. The glass or the plastic is transparent, but the water is not. So if you have, for example, like here an apple or any fruit that has been fallen down, you will see in near infrared, you will see a spot on it that you cannot see visibly because the water close to the surface or on the surface will be showing up. So again, water detection with the right wavelength, with a spectral filter, you can see through blood. So if you're a doctor and you're operating and you have an open wound and it's full of blood, like here, this is a heart or a part of a heart. This is dry, there's no blood, and here is 2 millimeters of blood. Visually, you would not see anything. With the infrared, with the near infrared camera, you can look right through it. Quite interesting as well, many paints, many oil paints or colors become transparent in near infrared. So this is red. These are all colors that are not transparent in visual light. In an infrared, you can just look through. So if you have a painting at home, you have your Van Gogh or whatever, and you want to check if it is real, if this is not a fake, then you can use a camera like this to see through the painting, and you also see what the artist originally drew underneath it, and then he painted over it. So things like that, art restoration, the cameras are used quite often. Now we speak about measuring temperature, high temperature with a near camera. This is possible. So I would say 90% of cameras today are uncooled microbolometers, traditional standard cameras for measuring temperature. Then you have some cooled cameras for high speed, but there are some advantages to use a near-infrared camera to measure temperature, but keep in mind the temperature has to be at least 250, 300 degrees so you can see something, and roughly 400 degrees so we can calibrate it. So if you have liquid metal, if you have any hot metal above 400 degrees, a near-infrared camera can be a good solution because, as you see here, that's, I don't know if you can read it back there, I will just read it. This is a 7 to 14 micrometer. This is a microbolometer, classic camera. You see the increase when the temperature goes up, the signal goes up. That's normal. But the more shortwave you get, this is a visual. This is the signal of a visual camera, the blue one here. And if you can look up there, you do not get any energy out of it below 400, 450 degrees. So this is the temperature when a metal begins to glow. So a visual camera can measure it. When we go in a shortwave camera, that's here, that's this curve, we are at roughly 250 degrees. So at this temperature, we get a little bit of signal out of the camera. It will measure, and you see the increase is immense. So just a little bit of temperature increase will bring us a lot more radiation. So it can lead to a much more precise measurement. What does it mean in reality? You have learned about emissivity. We know we want to have a high emissivity. We don't want a lot of reflections. And when you're measuring at metal with a long wave camera, this is a long wave, a mid wave, and a near infrared. With a long wave camera, just a small increase or decrease in emissivity can cause a huge jump in temperature. So you see here, temperature 100 degrees, 50, 10. So if we have an object that's, let's say, 3000 degrees, and we measure with a long wave camera, and we change the emissivity by 1%, so you have 0%, 100%, we only change it by 1%, the temperature can go up or down by 90 degrees. In a shortwave camera, at the same temperature, it's only 7, 8 degrees. So we are much more precise when we don't know the emissivity correctly when we use a shortwave camera. Keep that in mind when you have high temperature metal measurement and you want to be very precise. Typically the best solution is a near camera. So how do we do it? How do we measure? First of all, we need to apply a filter to get a little bit of the, especially the visual signal out, and leave more of the infrared, of the heat signal for us. So we apply a ND filter. If you read ND, that's typically a neutral density. That means it's just a filter that reduces over the whole spectrum of the camera, that just reduces the amount of radiation the camera sees or measures. And with all quantum cameras or all photon cameras, it's the same principle. We change the temperature range by changing the integration time. So when it comes to a microbolometer like we have it here, that's what we call a thermal sensor. So it's always exposed to the energy. It will always, let's say the temperature of 1 pixel will always follow the temperature that's radiated on it. So it changes the temperature a little bit. With a photon camera, we actually count photons. So we open an, let's call it shutter. It's an electronic shutter. We open it, we collect photons, and then we close it again. And if we do this 2.6 milliseconds long, we can measure 350 to 600 degrees, and so on. You see, if we go down to 1 millisecond, the temperature range goes up. The shorter the integration time, the higher the temperature. And here we put in another filter for the highest temperature. So this is how thermography or how measurement of temperature typically works. We have some radiation, we want to collect it. Either we heat up the detector itself, like with a microbolometer, or we count photons, basically. So how does it look in real life? We can look through a glass bulb. So this is the tungsten inside a glass bulb. With a camera like this, or the one we have outside, we cannot look through. We only will see the glass bulb itself, not inside. High temperature plasma. This is also a good application for a near camera. Anything that is very hot, laser welding, all sort of welding processes. So 3D additive manufacturing, like we have here. This is basically it's a 3D printer for metal. And to melt metal, you need high temperatures. And if you have high temperatures, you have the perfect camera with a near infrared system. Strip steel processing or molten steel. Don't get confused about the color palettes. In thermography, you don't have the right palette. You can use red, blue palette, you can use rainbows, you can use a black and white. It depends on the application and on what you want to do with your images in the end. So you will see black and white images in my presentation, you will see rainbow. Don't get confused, we're always speaking about temperature or heat radiation. Steel billets, so anything with hot temperatures. This one is also calibrated, so you can see 1,100 something degrees Celsius up here. And yeah, with the right calibration, you can use a near-infrared camera for this. Let's look a bit into the classical thermal bands. So that means from here on, you can measure -10, -15 degrees without any problem. And of course, at room temperature, you have plenty of signal on the detector. Again, we have our INSPI, indium antimonide. And so far, when you wanted to go fast, so the microbolometer, the uncooled camera, is quite slow. If you want to go fast, until a few years ago, everyone said, yeah, if you need long wave for some reason, if you want to measure spectral long wave camera, then you need to have MCD, cadmium telluride mercury, or mercury cadmium telluride. The disadvantage of this detector, if you switch it on, it's very noisy. You need to apply an external shutter. You need some correction methods. And what I have outside here, and I'm quite happy to have it here, it's an SLS camera. These are still very rare because the price is quite high, so they start somewhere above 100,000 euro. But the integration time is extremely short, so you can measure at room temperature with a very high frame rate, which is often not possible with an INSPI camera. So let's look about this in detail. We have an uncooled microbolometer here, same camera as we have here, just this one has a higher resolution. And we say you can measure up to 240 frames per second with this camera if you reduce the amount of pixels. Now that sounds nice on paper, but keep in mind this is not really measurement. We can record 240 frames per second, but if we look into the detail how the detector works, we will see the problem. You see here signal from 0 to 1, and you can see here milliseconds. So this is 10, 50, 100 milliseconds. Let's say at that point, we heat up our object very fast, or we move the camera into the field of view of our hot object. Like we have 20 degrees room temperature and our object has 100 degrees. And this is the detector that will follow, or 1 pixel of the detector. So it takes the detector like 30 milliseconds typically to measure correctly. Here it will measure some 25 degrees, here some 52 or something, and it takes quite a long time for the detector to really follow the signal. And this is every microbolometer, so keep that in mind. When you work with a microbolometer camera, you can easily go 20, 50 frames per second, maybe 100, but anything that's faster will lead to, let's say if we do 100 frames per second, that's 10 milliseconds per frame, and we are at 60-something%. So you still have a huge mistake in your measurement. So for any fast-moving object or any fast process, a microbolometer might not be fast enough, although it can record 240 frames per second, but it does not follow fast enough. So how does this look in practical terms? This is a microbolometer camera, a FLIR A600 series. And what you see here is a heater. This is some heating device. What you don't see, because the camera is not fast enough, there is a fan rotating in front of it. So this is a fast rotating fan. This camera will just give you a smear. You will never see the details. And if you want to see the details, because here we're speaking of an exposure time of 8 milliseconds, then we are somewhere here. So we would need at least 30, 40 milliseconds. And in that time, this part has already moved forward. So with a cooled camera, we have an integration time of 0.05 milliseconds. So you see we are, you can be tens, hundreds of times faster than with any microbolometer. This is how it looks. This is just a ball that's dropped, a falling ball. You will see the smear leaving behind. So it's not really one image. And this is a cooled camera, so you don't have any smear effects. This is an uncooled camera. And here I took some videos at home. This is just a lighter. If you're smoking, you know how this it does not repeat. So let's check it out. This is a microbolometer, and I think with the next one we can see it a bit better. Let's see if this one is repeating. I used the same camera with 240 frames per second. So what we will see, oh, this PowerPoint does not like me. Let's see if I can stop it here somewhere. Yeah. What you see are those fireworks coming out. This should be only one pixel or only one hotspot falling out. But instead, we see those lines here. And they are just because the detector is not fast enough to track one hot pixel, one hot spot. So the image looks nice, but we are never able to really recognize one spot. Now let's switch to a cooled camera, to a high-speed camera. And here it looks like that. Up. Too fast. It also does not play the speed I want it to. So I'll try once again. Let's take the next one. It's the same camera, but with a higher speed. And here you can see every part flying away, not just some smear, but really the part itself. Unfortunately, we cannot see. There is a very nice, like a galaxy moving up here, but it does not really show up on the projector. But again, high speed, short integration time, you will need a cooled camera. What does cooling mean? Cooling is, in that case, a quite complicated process. Most customers ask, okay, do I need a water pipe or something like that? No, we are cooling with an electrical system. This is, basically it works like your refrigerator at home, but we use helium as a gas to cool down the camera. So this is the cooling piston. We have the cold finger here, and in there's the detector. So this is a vacuum, a sealed vacuum chamber with the detector inside. Why do we need that? Of course, if you have an object that is minus 196 degrees Celsius and you put it on the table, it will immediately, water will not evaporate. Thank you. And then freeze. So this is why we have this chamber here, this vacuum chamber in front. It's cool, but it's not that cold, and the camera looks just through it like that. And it's a rotating system with typically 10,000 hours of lifetime. So about the cameras, again, I'm not going into all the details, just to give you an idea where the difference are. All of those cameras are cooled. Some of them only give you 60 frames per second. That can be enough. Why do we need a cooled camera when it's only the same speed as those cameras? Because the integration time still is short. So if you have an automated process, if you want to measure parts are coming through very fast on a conveyor line or something, you need a short integration time, but you don't need a very fast camera. You can choose something like that. And if we go up in speed, the camera I have outside will do 1004 frames per second in full frame, and up to 30,000 frames if we reduce the amount of pixels. Then there are, for long-range applications, systems like these. What can be interesting, you see a CG down there. When I started with FLIR a couple of years ago, again, it was ITAR here. So that means you need a license. It's a huge process. The cameras are produced in the United States. And back then it was really a pain to get all the paper through. You are not allowed to travel. You cannot even send the camera to calibration back to Sweden. And now this is all commercial jurisdiction. So we are no longer licensed as long as it's an industrial use. So it's a non-military use. We don't need any licensing. You can travel freely within the European Union and in most countries outside. So all cool cameras today from FLIR are license-free. Uncooled, of course, as well. So about wavelengths. I spoke about 3 to 5 quite a bit. This is where we usually specify the mid-wave infrared, 3 to 5 microns. And you will not be able to read it back then, but this is 3 microns. This is 5. So by the correct detector coating, we can form the detector in a way we want it, or the spectral response. Now we can use the same in-speed detector in broadband. Then we just leave out the coating, or we coat it differently, and it goes down to 0.8. So typically we specify the cameras from 1 to 5 or 5.2 micrometer. So you can have a broadband camera with the right filters inside to do spectral analysis. And the SLS camera I have outside, this is a long wave camera. So here we speak from 7 to some 10.5 micron. This is the typical response of an SLS. I'll show you the advantages a little bit later. The main advantage is the integration time still is much shorter when you have low temperature than with a mid-wave camera. So let's compare SLS to MCT. This is the classical long wave camera. You switch it on, it looks something like this. You switch an SLS camera on, it looks something like this. So the MCT still is okay, it's not a bad detector, but you need to do, when you do an external shutter, you apply some, let's say, blackened part in front, you press a button, and the camera, let's call it recalibrate. So it pulls all those pixels on one level. You need to do this with an MCT regularly, like every, maybe 2-3 hours. An SLS you can leave for days and it will not drift away. Speaking about speed, I already told you we are in the 1,000 frames per second area with a 640, sorry, with a 640 by 512 pixel camera, so it's a focal plane array. If we reduce the amount of lines, we can go up to close to 30 kilohertz. If you want to have a camera with a higher resolution, like a 1280 by 1024, so that's 4 times the pixels of our 6900 camera, it will never be faster than 6 kilohertz. So keep in mind, sometimes you have to decide, do I need the highest resolution or do I want the highest speed? Both is not possible. So the back plane of the camera, just to give you an idea how we can achieve this high speed. Apart from the inside, of course, usually we use a gigabit Ethernet connection. This is quite a fast connection when you want to transfer data on your computer from one to the other on your network. But keep in mind, when we operate this camera in full speed, we are producing in every 2 seconds, we are producing 1 gigabyte of data. So 500 megabyte per second. Gig E is not fast, not even close to fast enough for transferring that. So we use either Camlink, which is a standardized interface, or CoaXPress. So you can choose one of those interfaces to transfer in real time. But if you say you don't want to have a high-tech computer there, and you only want to use the Gig E Vision, it's quite simple. You use the internal RAM, you use the internal hard drive. So we operate it like a normal high-speed camera. If you have a high-speed visual camera, it will be the same. It has RAM inside. In this case, we have 16 gigabyte of RAM. We have our hard drive inside, and we can operate the camera from the normal Gig E. We don't need a fancy computer. We just record inside and then transfer the data. So what is 1,000 frames per second? If you have been here 2 years ago, you have already seen this. If you're here today, it's not playing. It's doing something because the mouse is, never mind. I'll show you outside if you like. It's just a drop of water, and I like it because it's so smooth, and it's not so smooth here, but never mind that. Yeah, why do we use, or why should we use long wave cooled camera, an SLS camera? We already compared midwave to an uncooled camera. So any midwave camera is much faster, much shorter integration time than a microbolometer. This is clear. Now we go, let's say 2 milliseconds when we want to measure around room temperature. -20 to 55, the camera needs 1.5, 2 milliseconds, depending on what type of camera, on the detector. If we go up to 90 degrees, we have already less than 1 millisecond, and so on. And here we are in the 18 microseconds when you want to measure high temperature, which is quite okay, which is nice. But if we look into long wave, we keep in mind that 2 milliseconds at the lowest range. If we go for an SLS camera, this is even an older type. The newer ones are even faster. At room temperature, the lowest range, we are at 0.16. So we are already more than 10 times faster, shorter integration time at low temperatures when we use a long wave camera. So it does make total sense to, for applications at room temperature, at low temperature, to think about a long wave cooled camera. And again, the housing is the same. So we have the same speed, we have the same device, the same camera housing, but a different detector, a different sensor. So this is our SLS long wave. Here it's looking a bit different, but it's basically the same. We have our wavelength here. We usually don't use the area between 5 and 7 micrometer. I think you have heard in the first speech. This is mainly because of the environmental disturbance. We have water in the air around us, we have CO2, and most of those gases that are not transparent are in this area. So if you would build a camera at 6.5 micrometer, you will not be able to measure more than 5 meters away, 10 meters. The camera will be blind. So this is why we use either the area below 5 or above 7 micrometers. And about the material again, INSPI for midwave, this is typical today, and SLS is now stepping in to be the future of long wave cooled cameras. How does it look? And I really hope the video works now. Yes, this is an ice cube. So what do you do when you're a thermographer and you need something very cold that moves fast? You use an ice cube and you use your hammer to crash it. And this is what I did here. I'm starting it again just to give you the idea. On the left side, we see an SLS camera, so the long wave, 95 microseconds. So you can measure an ice cube with an integration time of 95 microseconds. If you had told someone 10 years ago that a cooled camera will be able to do this, he would have told you you're crazy, because usually you use about 1 microsecond, so it's much longer. What do we see now? The fast-moving parts in the focus. Keep in mind, don't look in the out-of-focus area. That will be blurred, of course. But in focus, it's crisp, clear, it's not smeared. And when you look at the already very fast midwave camera, there's a lot of smearing. Now let's look at the video again. And here you see very crisp image, and on the right side, a lot of smearing. The faster the part moves, the same as we had before, the faster the part moves, the more tricky it gets to really see it. Okay. And then there is another differentiator between different types of cameras. So we have our A series that is not so fast. The main reason is we need a long integration time. this camera has a 15 by 15 micron pitch size. So each pixel on the detector is 15 by 15 micrometer. You can compare this. You have your cell phone and you have a 12 megapixel camera inside. And then you have a professional camera like we have it back there, also with 12 megapixels, but the difference, the image is much better, especially at low light conditions, because each pixel is much larger. So your whole cell phone has a detector that's this size, and a professional camera has the same resolution at that size. And the same goes here. If we have more area per pixel, we can collect more photons. We have a shorter integration time, a better picture, a better image. And exactly this is the difference. There are detectors on the market with 10 by 10 micrometer. They're very noisy. They are very they're high resolution, but the image is not very good. And this is what we choose for our low-end, still good cameras, but less expensive cameras, a 15 micron. And for the X6900 is a 25 by 25 micron. So you see the amount, or the size is 6 times per pixel. Yeah, some comparison. I don't go through all the comparisons because I want to stick to the time plan more or less. But what always what always brings in or shows up the same, the microbolometer is much slower than any cooled camera. This is the main thing I want to say today. And yeah, again, we're not talking about all the numbers. Just keep in mind, the fastest one is a cooled long wave, then you have a mid wave cooled, and then you have the long wave uncooled as the slowest camera. So one or a few slides now about the temperature range. If you, we can go back, I can just show you the temperature range is also an issue. The first temperature range, at 2 milliseconds integration time, the detector, the mid-wave detector, can measure from -20 to +55. What does this mean? Below -20, the detector will flatten out, so the signal change will not change anything in, or the temperature change will not change the signal. Then we go up to 55, and at some point the detector gets saturated. So even if the temperature still goes up, the detector will not show any increase in signal. So this is why we're limited to -20 to 55. Let's look into a long wave cooled camera. Here we have -20 to 150 in just one range. So we already have a much wider range. Then we change the integration time, 55 to 350. With a mid-wave camera, to get from 55 to 350, we will need 1, 2, 3 ranges. So FLIR does have some technology where you can operate a camera to take one image at that integration time, the second one at that, and the third one at that, and then add all 3 images according to the detector, let's say, signal resolution. So we can get one image from 35 to 350, but it will take a bit of time. And if you have a fast process, the car is moving by, you take your first image here, the second here, the third here, you cannot really stitch them together, so it should be more or less stable. With a long wave cooled camera, we have a very wide range without changing the integration time. And this shows up in the image I wanted to show you here. With a mid-wave camera, 3 to 5 micron, we have a lot of saturated signal here, also a bit of blur already, because the signal is so high that we will get some influence on the whole image. So this is fully saturated. With an SLS camera, you still see the people down there, you still can recognize them, but you have no, you have saturation. These are heating, you know, those gas heaters. I think it's the same in Czech. In Austria, we're not allowed to smoke inside bars or restaurants anymore. So people go out and they stand in winter and they smoke outside. And those things, they get quite hot and they radiate a lot of energy. So this is just to show with a long wave SLS camera, you have a much wider range without getting saturated. So this was the setup. It's two X6900s like the one I have outside here. So this is quite some pricey equipment they put together, and they synchronize the, basically it's multispectra thermography, but it's not overlaid. And one last thing when it comes to long wave cameras, this is, you know, that's an American company, they like to blow something up. And here they filled the bottle with flammable gas. And I set it on fire. Let's see. Should be able to play. It does not. Okay, once again, I can show you outside. We would see two things. First of all, this bottle is transparent in midwave infrared, so it's a plastic bottle. So we will see inside, we will get saturated immediately here. And then you see the flame coming out. So it's quite a view. I can show you later if you jump by. Let's try it again. No, never mind. And with the SLS, we are not saturated. We can more or less measure the gas, but still have all the background on it. As a very few, I think you are going to talk about, Jan, you are talking about gas find. So I will not, or is it planned?
You can talk about it.
Okay, just a few minutes, 2-3 minutes. How do we do optical gas detection? We use a camera with, in that case, it's also a cooled camera because it's very sensitive. And we use a small spectral filter. So we don't use the 3 to 5 micron camera, but we only use a few 100 nanometers of bandwidth to only show the camera the small part of the spectrum where our gas is emitting. That can be natural gas, that can be any, usually it's inflammable gas. It can be SF6, so the insulation gas. We can detect visually with the camera. And it looks, again, if we are lucky, we have a video. Otherwise, okay, we're not lucky with the videos today. But you see the cloud a little bit here. So this is, optical gas imaging is always better with a moving image. So with something that's changing, because you see the cloud going up here. And the last part I wanted to show you was a live demonstration. And if you like to come to the front, the idea, I just wanted to give you an idea about the touch and feel of those cameras today, especially compared to the past years. Many things have changed. It's much more flexible. We do have our touch screen now, of course. Continuous autofocus. What I wanted to show you first of all, I should switch the laser off. So we use a laser rangefinder to measure the distance to the object and constantly change the focus point to what the laser gives us as an information. Since it's multispectral, one thing I wanted to show you was our function MSX. And I have to stop the recording here because I cannot switch everything while I'm recording, but never mind that. So what we have now, maybe you can see it, this is classical infrared image. It's the color palette is rainbow, and of course the camera has also a visual camera inside. So this is our normal digital camera. I hope you can see it as well here. Yes, if you don't see anything, just let me know. I'm not sure if I can see the same thing. Now, this is a function that has been on the market for many years, picture-in-picture. You take your infrared image, you put it in the middle of a visual, looks nice, quite okay. But if you want to go further, then you use MSX. I don't know if you can see the difference. I will look at an object that is not so, let's say, that doesn't have so much contrast. I'm looking at my laptop right now, and if you can recognize it, you can see the writing on the laptop. Now let's switch off MSX. This is the normal infrared image. The laptop display is the same temperature everywhere, so you don't see any big difference. and if I switch MSX on, it's basically multispectral. We use the visual camera information. We look for any signature in there, and we overlay this. So this is a very nice function to be able to read with an infrared camera, because this is something you cannot do if you switch it off.
Is it a combination of RGB and color?
Exactly. We use the RGB channel, do some image not image recognition in that, but we are looking for borders and so on, and we just overlap them without disturbing the infrared image. So this is a function that is today in all of our cameras. So this is with, and this is without. Very nice. If you look into an electrical cabinet, you can read your writings and everything. You can see more detail. Now about setting up the camera. Usually when you want to change temperature and range, you use a joystick and you play with it for 15 minutes and then you have some image. With a touch screen, it's much more convenient. You have the slider on the right here. So I can use it like on a cell phone. I can slide in, or slide up, slide down. And if I press on any area, if I want to say the temperature here is interesting for me, I press on it and it will focus the temperature range on exactly this area. So this gives you a much easier, I'm just pushing the touch screen now, a much, starting recording again so we can use it in our video later. So just by touching on an area, the temperature range will be automatically scaled. And again, we have the slider here. Of course, we can put in spots, areas, lines, whatever, using the touch screen. So this is quite a nice view. This is the new T860 cameras. It's the 640 by 512 camera. And again, I have it outside, so if you want to have a look at it, just come visit. So this ends my presentation. Do you have any questions? A lot of numbers, a lot of information. I will be...
And the most obvious question, since the Christmas is coming, how much is that camera?
Christmas is coming is good. I just bring you a very nice Christmas present. This is for friends and family. This is to attach to... I'm sorry. Okay. So the question was, Christmas is coming, what is the price? Okay. So this is for everyone to give away. It starts at 250 to 400 euro. This is attached to your cell phone. It's already a fully featured camera, infrared and visual. So for toying around, this is a nice one. And the professional camera starts at roughly 1,000 euro. And when it comes to those, it depends on the resolution. So it starts at, in a similar form factor below 10,000 euro with already high resolution, and goes up to roughly 25,000 for this class, and above 30 for the even higher resolution. And if you're looking for a cooled, high-speed, long-wave camera, you can get a very nice car for it. So a very, very nice car. So 150,000, something like that.
My girlfriend will not like it, but I'm hooked.
Yeah, let's talk outside, and she will not know. Thank you.
I actually have another question.
Yes, please.
So I noticed there was a microbolometer-based sensor mentioned in the presentation, but cooled one, I believe, by Peltier cooler. So what are some benefits of those? Does it improve the speed, or maybe the sensitivity or dynamic range, or what?
There was Peltier, basically not cooled but stabilized detectors until 3-4 years ago. So they're fading out now. Today we are in a techless state. I would say all cameras today. So I don't know any manufacturer who still uses the Peltier. The reason was quite simple. If you have a thermal detector, so if every pixel heats up when you increase the temperature radiating on it, And by heating up, cooling down, the detector was drifting all the time. It still is, but today we have the possibilities to get rid of that electronically. So we can stabilize the camera quite well by measuring several spots inside, and the Peltier is no longer required. So it drew a lot of energy, and there were some disadvantages, so they tried to get rid of it, and today at least all FLIR cameras in microbolometers are techless, so no more Peltier stabilization.
Okay, thank you.
Thank you.